Hi everybody, my name is Petr Lorik and I work for Freescale. We happen to be a partner of ARM, so it's good timing. The order of the presentations is great. Um, what I will talk about today is an introduction to the topic of a different type of tracing that some of you may not be familiar with, and that is tracing that is focused on the needs of the systems which process networking data. I'll talk a bit about the type of trace data and the type of performance analysis tools that we have developed at Freescale, and about how some of the requirements that we have, we think will apply to the Linux community. These are the main topics that I want to talk about today. I'll talk a bit about what is a network processor and about why we want to analyze it in a way that's different from a generic Linux system. I want to talk a bit about the hardware trace support that is sometimes necessary to analyze these network processors. I'll talk about the software trace and how we are going to model and visualize this data that we're going to get from all these various sources. And if we have time at the end of the demo, at the end of the presentation, I'll try to do a quick demo of the tool that we have today. So in a nutshell, a network processor is a device that has been designed to process network packets. You'll find these things in routers, in base stations, on the cell phone towers, and so forth. And what these things typically include is their SoCs, their systems on chips, and they include a set of general purpose cores, and also they have some specialized hardware that is used to offload some of the networking tasks from software to hardware. And I'll talk a bit about how one such network processor architecture looks like to support the explanation of the concepts that I'm going to present. Okay, so the question is, why do we have to analyze things in terms of network packets? And on this slide, I try to outline the main reasons why we want to do that. The problem is that the software analysis tools that exist today, such as the software debuggers, the profilers, and the tracers that we have talked about today, they don't know, they're not aware of the network packets. They're agnostic to that. And to a large extent, the same thing happens with the hardware-based tools. The hardware designers, they can design performance counters in the system. They can give you all kinds of hardware trace data. But again, those things are not going to be closely correlated with the networking data that flows through the system. So that's what the problem is. So from the point of view of somebody who is a networking developer, the F-trace data, the LTTNG data, and so forth, looks like low-level data. So we have to find a way to present the trace data that we can get from such systems by using all these different methods in a way that is much closer to the needs of somebody who develops networking applications. There's also a set of networking tools, such as Wireshark, for example. Now, these tools, they tell you what happens with the system when the system is seen from outside. Okay, so they'll be able to tell you what is the throughput on a particular interface, or what are some statistics that have been computed by looking at the log of the network packets. But these tools, they don't give you any insight into why you only had 50% of the throughput that you were expecting. So this is why we believe that there is a need for a new type of tools, and that is tools which are focused on the networking data, on the needs of the networking application developers, and also tools that give you insight into into what happens with those network packets once they reach the SoC hardware or the software that is running under Linux on the general purpose core of that device. And of course, we know that none of these tools can possibly solve all the problems of those users. Therefore, we have to make them in a way that makes it easy for these tools to be integrated with other tools. These are the main use cases that we are targeting. Oftentimes, those who develop applications for networking, they simply want to trace their packets in the system so that they can confirm that the data flows on the expected paths. Or they want to understand why they're losing packets in the system. The packets may be discarded because there's a QoS, there's a quality of service application, for example. And sometimes that is not clear at all. You simply have no idea why the packets appear to simply be destroyed at some point in the system. And there's also a bunch of other use cases that you can see here on the slides. We want to allow users to measure the networking metrics, such as the throughput or the packet dropout rates. We also want them to be able to measure the latency of processing those packets in the system. And also, we want them, in the case when the system is a multi-core system, we want them to understand very easily how the networking loads are being balanced in the system. So these are the main issues that we have been faced with when developing tools for networking processors. Number one, the software trace, the F-trace, LTTNG trace, and so forth, that is insufficient when a lot of the networking functionality is offloaded to hardware. Okay, the software is simply unaware of that. The other problem is that in these multi-core systems, the data has to be collected from multiple sources. You have to be able to correlate the data in a meaningful way among those sources. And finally, you have to be able to visualize that data in a way that is effective. The other problem is that in the systems, at least in the systems that we have been dealt with, those systems happen to be very complex. And therefore, simply managing the hundreds of trace settings is a non-trivial problem. And finally, you have heard in the presentation from ARM, there is a problem when you try to collect too much trace data. So therefore, you have to be able to control what data you collect and when you collect it. On the next few slides, I'm going to present the work that we did, and we have called this tool the Freescale Packet Analysis Tool. And these concepts that I'm going to discuss here, I think that they apply to other situations as well, not just to Freescale Silicon. Now, our tool, in essence, is a very user-friendly tool that uses the hardware trace from the Freescale devices, and it therefore allows us to collect that trace data in a non-intrusive way or with low intrusiveness. And after we collect the trace data from the devices, we are presenting it in a way that is very packet-centric. In a nutshell, this is what the architecture of the Freescale devices looks like. I'm not going to go into the details. All you have to know is that there is a bunch of cores. There is a system bus, which we call CoreNet, the light blue bar. And there is a central data exchange mechanism, which is called the queue manager. And once the packets arrive from the network, they're being handed off to the various cores in the system or to the hardware accelerators, such as a crypto accelerator, one piece of hardware that knows how to encrypt or decrypt packets. And all of those data exchanges happen via this central data exchange mechanism called the queue manager. So the hardware trace that we use for our tool, what it does is that it is, number one, it's based on something called the IEEE ISDO 5001 Nexus. This is a Freescale's hardware trace solution. And what the trace data does is that for every single packet that we trace, we get some information about how that packet was processed while inside the hardware. And that means, for example, if the packet had to be dropped, we do get an indication of that, and also we do get the reason why the packet was dropped. We do get the ID of the trace point. There are multiple points in the system where the data gets collected, where the trace data gets collected, and therefore we have to get an ID, a unique ID for every point in the system from where we can get the trace data. And of course we get timestamps from a hardware clock. Now, the content of the packets, meaning the packet headers and the payload, that does not show in the trace data. I'm going to skip ahead a little bit here and tell you very briefly why this tool is useful. What I have here on this slide is the output of two tools. The top part of the slide contains the output of iPerf, which is this little open source application that you can run to measure the throughput on a network interface. What that tells us is that there's a 25% packet loss. But the tool does not tell us anything about why that happened. And when we use the packet analysis tool, which is on the screenshot here, we get to see very clearly that the packets have been processed on two different processing paths, and I'm going to explain what that means in a few slides. And we can see that